Ladies and gentlemen, good morning. I'm Gianfranco Cerofolini, and my current address is the University of Milano Bicocca, but most of the original work I'll present was done when I was working with ST Microelectronics. All the matter the structure of my talk is formed by a short description of the evolution of the current evolution of microelectronics and its limit, how these limits can be overcome in the next 10, 20 years, and in more detail, how the tool necessary for that, the crossbar, can be produced at on the nanoscale length. And I'll show briefly how sublithographic feature can be contacted with lithographic method. At last, I'll spend a few words to show how nanoscopic objects can be functionalized to impart to them wanted electronic behavior. It is just the opposite. Sorry. Okay. All the matter starts with the observation by Moore of the evolution of electronics. We have observed in the past 30 years that the density that the complexity in terms of number of bits per unit area that can be inserted in a circuit has increased exponentially with time over a period of approximately 30 years. The current rate of increase is of a factor 2 if 18 months for memories, or 2 years for microprocessors. This process has been virtuous in that the cost of a single function of a bit has decreased exponentially, in this way allowing a larger and larger market. And the fall for the evolution of electronics has been just the loss of the decrease of cost per bit. This process is expected to stop in a time still to be clearly understood which time, due to several factors. Physical limits are expected to limit the shrinking of the device. Technological limits may be important, and even economic limit. It is indeed well known that when the size of the basic constituent of electronic devices, the metal oxide semiconductor field effect transistor, is strongly affected by short channel effects, it is difficult to switch off a transistor with external voltage. From direct tunneling, the passage of electrons from the channel to the insulated gate, and from intrinsic statistical fluctuation from one device to another. At this moment, the threshold voltage of a single MOS in an integrated circuit is controlled by really few, of the order of 1 atoms. So statistical fluctuations are very important. Nonetheless, the MOS FET is expected to work down to a gate length of 10 nanometer. This has been proved, for instance, by Intel, but any company has its own roadmap, showing that really small devices with gate length of 10 nanometer in that case continue to work as FET. The problem is not to produce single demonstrator that can be done in the lab, but to develop a technology consistent with the new size. Shrinking the device size was relatively easy until the size of the gate remained higher than the wavelength of the radiation employed to define the geometry, but became progressively more and more difficult when the size was reduced below the wavelength. It may seem physically impossible to do that, but the difficulty has been removed, increasing the complexity of optics, employing the evanescent wave, employing interference effects that increase the concentration of the power in a half wavelength, and so on. But the cost of this process has increased dramatically. This is the typical cost of the tools required for the production of thinner and thinner lines. At present, the most advanced photolithographic tools have cost of the order of 30 billion euros, with spare parts per year of the order of 30% of the total. Taking in mind that a number of such tools are required for the production of devices, this implies the economic limit. In green, in orange, we have a projection dated 1991 of the cost of a fab required for the production of integrated circuits. In green, we have, on the contrary, a consumptive datum. And this comparison shows that it is notoriously difficult to predict the future, first of all. But even taking the most conservative increase, we see that in a few years, the cost of a fab will greatly exceed 10 billion euros. That would be practically impossible to all operators, except perhaps in the next 10 years, Intel and Samsung, and in the next 15 years, nobody. So if we intend to go down with size, we have to develop new architecture and technologies. And the most promising one is the crossbar technology, which is essentially a structure, an architecture formed by a wire array, shown here in a plane, separated by an upper array oriented perpendicularly to the previous one, by an electrically active substance able to perform electrical function. So the predicted architecture which should overcome the current limits is formed by an integrated circuit with TSI, terascale integration, 10 to the 12 bits per square centimeter. Is formed by a conventional CMOS circuitry, hosting a very dense nanoscopic crossbar, in turn hosting in each cross point nanoscopic cells. Of course, if the production of cells requires the same difficulties as the production of the MOSFET, display has no meaning. And one way to solve the difficulty is to use as an active element simply molecules. And a lot of molecules have been identified to have interesting electronic properties. First of all, the ability of presenting in a reprogrammable memory, which could be used to define memory states. Hence, the specialization of the crossbar approach is so done. The hybrid TSI IC is formed by a conventional CMOS circuit hosting a nanoscopic crossbar, in turn hosting reprogrammable molecules. And the structure of the architecture is shown here. Here I have the CMOS, conventional silicon-based, hosting the crossbar, lower array oriented in n direction and upper array oriented in the perpendicular direction, in turn hosting molecules by themselves able to perform electrical function. This idea requires essentially 4 steps. The setup of an economically sustainable technology for the preparation of at least 10 to the 11 cross points per square centimeter. The ability to insert in the cross point region, not by single processing like STM or AFM, but by batch processing, the functional molecules able to perform electrical functions. The multiplexing of the nanoscopic crossbar, where the separation is not accessible with standard lithographic method, and the design, synthesis, and characterization of the molecules. The first attack to this problem was done by a collaboration by Hewlett-Packard and the University of California at Los Angeles. In their approach, they deposited and defined a lower array in yellow here, over which they deposited via Langmuir-Blodgett technique an oriented layer of molecules, of reprogrammable molecules. Such molecules have 2 functions. First of all, they behave as spacer for a second layer. Second of all, they should be able to perform the electrical function. After that, there was a deposition of a metal they called the passivating layer, over which they deposited a second metallic layer and defined it. And the new feature was used as a mask for defining the crosspoint. The crosspoint, so, is formed by a wire separated by an upper wire perpendicularly oriented by a set of molecules with the function of spacer and with electrical properties. The idea is fantastic, but it did not work, essentially because in this step, okay, the deposition of the metal layer, the deposition was necessarily PVD, because the organic that does not tolerate high temperature processing, and the initial stages of the process were characterized by the impingement, by the deposition of atoms ones by ones. So they, rather than forming a compact film, they decorated the molecule, so being responsible for leakages and unwanted electrical behavior. The basic idea in which I moved instead was based on the construction first of the crossbar, and after that in the insertion of the molecules in the crosspoints. The crossbar, I remember, should be done at density much higher than the ones achievable with the current lithography. So we have to develop method for that. And there are essentially two methods for preparing ordered arrays of wires with sublithographic features. All of them are based on the transformation of a vertical feature, which can be controlled on the deep nanoscale region, into horizontal feature. And this is done essentially in two methods. This method was developed by the University of California collaboration, and essentially is related to the formation layer by layer of materials with different etching properties. In particular, this may be silicon, silicon dioxide, silicon, silicon dioxide, grown horizontally. After that, the sample is cut perpendicularly, and one of the two layers is removed by selective etching. This structure is used as a mold to impart on a underlying structure, on an underlying layer, the same pattern, or the same original pattern. In this way, we have transformed thickness in width. The cost, of course, is that we have to manage and work in a mechanical way the samples. The other approach, instead, can be done on the wafer, then working separately on the mask, and essentially is an old process of silicon semiconductor technology. Starting from a substrate here and depositing a sacrificial layer in light blue here, it is defined by, in a vertical way, by a very high aspect ratio with conventional techniques. After that, there is a deposition, a conformal deposition of a wanted film. So silicon technologies is able to deposit the three major films of that technology in that way: silicon, silicon dioxide, and silicon nitride. The other step is the totally directional etching of the layer, simply by spattering. What remains is a sidewall of the in red here, extended below on the side of the original seed. A selective etching of the original seeds leaves this feature, which has the same width as the original thickness. This is an example taken from the Berkeley, showing that the features of 20 nanometer can be easily obtained. Actually, they showed features of 7 nanometers reproducibly produced. My idea was simply to reiterate the process. Here I'm showing a free repetition of the process for the original seed, conformal deposition, spattering, second deposition, spattering, and so on. In this way, I can obtain an array, and that it is not a dream, it is manifestly shown in that case, where an array with a pitch, with period of 35 nanometer was produced. And it was produced simply at the second attempt. So it is an easy process. It is costly, of course. Coming back to, in that case, I have to perform a deposition, an etching, a second deposition, an etching, and so on. The process, however, can be used in a multiplicative way, for which the number of steps required for that is greatly reduced. And this is an example of how that can be done. So we have produced in the previous examples an array with separation of 30 nanometers. When I worked on that idea, the minimum achievable length obtainable with standard lithography, with advanced but standard for semiconductor industry lithography, was 100 nanometers. So how can separate wires so close? The idea is very simple. It is sufficient to cut with an angle sufficiently low, and there is an enlargement of the open region in such a way that can be accessed. Of course, I spend, but addressing n by n square cross points requires simply 2n contacts. In this way, the number of the wall density is controlled by the cross-point density. I conclude showing in a very compact way that once the cross-point has been obtained, it can be, by suitable control of hydrophobicity, hydrophilicity, and so on, of the silicon surface of the wires, it can be functionalized to have in the inside region electrically working molecules. This is the list of my past and previous and current collaborators. Thank you.
Thanks again, speaker. And we are a little bit late, but if there are some questions, and then we will move to the conclusion and general remarks. So first, any question related to this last talk? Yeah.
I did not catch one thing. Are these crossbars you showed at the end independently addressable? Each node is independent?
Yes, I can, reducing significantly the complexity of the problem, I can also reduce the number of contacts. But in that case, it is required a given order of reading. In that case, I can address any wanted cross point.
Which molecules do you have in mind?
The question is difficult. The question is difficult because the most conservative approach is to use essentially rotaxane, the ones employed by the HP-UCLA collaboration. But industry is very conservative, and in my opinion, if the crossbar will win the battle for ultra-high density, the first functional material to be inserted will be inorganic, like phase change memories or phase change alloys or something like that. The idea of the crossbar, of the cross point, is that it eventually allows managing in a batch way single molecules. So in a way, it could give the ultimate density achievable.
So if no other question, we thanks again the last speaker.